Thanks for watching the screencast. The objective of the screencast is learners will be able to solve quadratic equations of the form x squared plus bx plus c equals 0, where b is even, by completing the square. Before we complete the square, you need to know this square root property of equations. The square root property of equations says that for every c, which is an element of the real numbers, in other words, for every real number c, if x squared equals c, then there are actually two values that make the equation true. One of them is the square root of c. The other is the opposite of the square root of c. So here's a quick example. If x squared were to equal 100, 100 is a real number. There are actually two numbers that make that equation true. One of them is x equals the square root of 100, which is 10. The other one is x equals the opposite of the square root of 100, which is negative 10. So this property is one that I know you saw when you took Algebra 1. I imagine it came up at times in geometry, but we're going to use it today as well. We're going to use it to solve some equations that are a little more complicated than this one here. One of the equations that we'll solve with this is this. X plus 4 squared equals 25. And I can apply that square root property of equations. If something squared equals 25, then I know that there are two things that this something can equal. One of the things that something, x plus 4, can equal is 5. Another option is that something, x plus 4, could equal the opposite of the square root of 25, negative 5. And of course this leads to two solutions. One would be x equals 1. The other would be x equals negative 9. And if you do a quick check, both of those values will solve this equation. 1 plus 4 is 5, and 5 squared is 25. Negative 9 plus 4 is negative 5. And negative 5 squared is 25. So those both work. Here's another example of the square root property of equations. If x squared plus 9 equals 0, this isn't in that form x squared equals a number yet, but I could rewrite it this way. X squared equals negative 9. Now, until you saw in the previous learning target us solve a problem here, we would not be able to say this equation had any solutions. And it's true that this equation doesn't have any real solutions, but it does have complex solutions. Because if x squared equals negative 9, then x can equal the square root of negative 9, or x can equal the opposite of the square root of negative 9. Right? That's just an application of the property as it was written at the top of the page here. If x squared equals some number c, then x equals the square root of c, or the opposite of the square root of c. Well, the number in this case for c is negative 9. So that makes the problem a little more complex, no pun intended, but we can still solve this. The square root of negative 9 is 3i, yes, where I is the square root of negative 1. And the opposite of the square root of negative 9 is negative 3i. So even equations that you couldn't solve in Algebra 1 can now be solved as long as you're willing to accept complex solutions. Okay, here's the main event of this screencast. We want to be able to do a procedure that's called completing the square. And to complete the square, you need to be able to find missing terms in what are called perfect square trinomials. So what you're going to see here is a prompt that says, can you find the missing term to complete each square? X squared plus 6x plus what equals something squared? This setup is similar to that box method for multiplying and factoring that I teach in Algebra 1. It's super useful for completing the square. I want to show you a little bit of why this actually is used to complete a square. I know from my factoring concepts that x squared could factor to x times x. And I know that if this length is x and I'm looking to fill in 3x here, I need like a positive 3 here. And I believe you could say the same belongs here, because here you would need 3 times x to get 3x. The reason that I know this is a square is whatever x stands for, x plus 3 is going to be the same length here as it is here. No matter what value of x we have, this shape is a square. The sides are all the same length. So what number is missing here? The number that goes right here, the number that's missing, is also the number that belongs here. What number is that? Well, it's 3 times 3, it's 9. So 9 is the number that's missing. 9 is the number that completes the square, makes this whole figure a square. And because 9 is the number I need here, I can show also that that means that this same expression, x squared plus 6x plus 9, means the same thing as what squared? This times this squared, it's x plus 3. So the number that completes the square is 9. And because it completes the square, I can write my whole expression now as x plus 3 squared. Let's try the one over here. We've got x squared plus 14x, which I've split evenly into 2 pieces because I want to make a square. X times x is x squared. Here, to multiply something by x and get 7x, I guess I need positive 7. And I suppose I could do the same thing here. What times x gives you 7x? Positive 7. And I think that actually tells me what goes here. X plus 7, the quantity squared, is what I'm seeking. So what is the number that completes the square? Well, it's 7 times 7. It's 49. So I've got this list of steps here for actually completing the square to solve a quadratic equation. And I'll quickly address them. You can always scroll back to this point. This will be about the 7-minute point of the video if you need to see this list again. Get the equation in lowest terms. If something can be divided out of each term, do so. That's not something that you have to do, but that's something that makes it a little more convenient to solve the equation. Get the x squared and x terms on one side of the equation and the number term on the other side. That is actually a different move than the one that we usually seek for solving. When we solved by factoring, we wanted all of the terms, a, b, and c terms, on one side of the equation. You're going to complete the square, and then once you've done that, you will have an equation that you can use the square root property of equations to solve. Let's do one together. I want to solve the equation n squared plus 10n minus 39 equals 0, and I want to make sure I do it by completing the square. There's nothing common to all of the terms that can be divided out, so I don't need to worry about that step here. My next step would be to get the n squared and n terms by themselves, and the number term on the other side. So let me take this 39 term, move it over here, and rewrite it as a positive 39. Now, it's been my experience. I know that I need to put something in here to complete the square. I'm going to leave myself a little bit of space. Okay. So what I'm seeking now is the number that will complete the square on the left side. N squared plus 10n plus what? And I still sketch out that square diagram that you saw earlier in this screencast. That still helps me solve this problem. So I've got n squared, which I know will become n times n. My 10n, if I'm making a square, I need to split the 10n equally here and here. So how about a positive 5n both places, which would make these plus 5s. So what number is it that completes the square here? It's 5 times 5. It's positive 25. That's the number I need to add in here. But wait, you can't just take an equation and add 25 to one side of it, can you? If I add 25 on the left side of this equation, I'd better do it on the other side as well. I'm not allowed to break that equation, the property of equality, the addition property of equality. I've got to, if I add something to one side, I've got to add it to the other side as well. So here's where the magic starts happening. On the right side, I now have 39 plus 25 is 64, I think. But on the left side, I've shown with my diagram what I can do with n squared plus 10n plus 25. I can write that as a binomial squared. And what is that binomial? What are we multiplying by itself to get n squared plus 10n plus 25? It's n plus 5. Yeah. n plus 5 squared equals 64. And I can now solve this with that square root property of equality. If I think about something squared equaling 64, then either that something equals the square root of 64, 8, or that something equals the opposite of the square root of 64, negative 8. And I can get my two answers. This one lends me n equals 3, and this one gives me n equals negative 13. If you want to check, those both do solve the original equation. Okay, I'd like you to pause the video. I'd like you to see if you can solve this one by completing the square. And when you get an answer you like, or if you get stuck somewhere along the way, hit play to get some feedback. The very first thing I need to do to solve this is I need to deal with this 25, which really shouldn't be on the same side as the x squared and the negative 6x. Let me rewrite this equation as x squared minus 6x, I'll leave a little bit of room here on the left side, equals negative 25. Okay. But now I need to figure out what number needs to be added in to complete the square on the left side. You don't need to sketch this puzzle out, this little box diagram out. You're probably able to do this without, but it's a good tool to use if you're not sure what to do. X squared means I'll get x and x. I'm going to split my negative 6x evenly because I'm making a square, so I'd better do negative 3x here and negative 3x here, which makes the numbers that are the second term of my binomial negative 3. So what number is it that completes the square? Well, it's whatever negative 3 times negative 3 is. It's positive 9. And that's the number to complete the square of the left side of the equation. But of course, if I add it to the left side, I also have to add it to the right side. So what do we have? Well, on the right side, negative 25 plus 19 is plus 9 is negative 16. And then I know that the left side, I know I can write x squared minus 6x plus 9 as x minus 3 times itself, x minus 3 squared. There we go. And now I can use the square root property of equations to solve this equation. I can take, if something squared equals negative 16, then either that something equals the square root of negative 16. What is the square root of negative 16? It's 4i, that's right, yeah. Or that something, x minus 3, would equal the opposite of the square root of this number. The opposite of 4i, negative 4i. I can solve both of these equations for x as well by adding 3 to each side. But if I add 3 to 4i, I'm just going to get the complex number 3 plus 4i. Don't make it 7i, right? Only the real and the imaginary parts would combine. This equation, if I add 3 to both sides, would give me 3 minus 4i. And there are my two solutions. Thanks for watching.